Good afternoon, everybody. Welcome to the second in our Harper Virtual Roadshow series. Today, we're going to focus on color. Color is a vital part of all our lives. We've been hardwired from beginnings of time to accept different meanings associated with different colors. Green was Mother Earth, a safe place, go forward. Red typically was fire or danger or stop. Yellow was some version of caution or alert. All these have been, like I say, hardwired into us. These things are still in use today in traffic signals and everything else. Lots of other colors are associated. White is typically associated with something being clean. Black is dirty. Red is exciting. Blue is calming. The list goes on for all these different colors. But in today's marketing world, color is huge. The psychological impact that I mentioned has been studied and applied to all facets of our everyday lives. Fortune 500 companies have spent millions of dollars determining what their brand colors are going to be, and then what they go to great lengths to ensure those colors are reproduced to exact tolerances time and time again. And the same goes on for college team sports. Go to a University of Clemson ball game wearing a University of Texas or a University of Tennessee orange shirt, and you're not going to be welcome there. They are all three orange for sure, but they're not the same color of orange, and they're very particular. Today, we're going to discuss color theory, color order, color terminology, pigment selection, viewing the colors, toning inks, and communicating colors to others. Once we've matched these colors, we have to be able to communicate that to other people to share the colors. So some of the first things we'll talk about is color terminology. And one of the first things is hue. When we talk about color, the most obvious thing is the hue. Um, Albert Munsell did a lot of work back in the late 1800s and early 1900s in organizing the colors into where we see them now. All the calculations were done by hand with logarithmic math, no computers back in those days. Now, his main focus then was on the order of colors. And his calculations led us to realize that the visible spectrum of color was arranged in actually a spherical shape. So we now call them color families: red, yellow, green, and blue. It's important when describing color with others that we're all using the same terminology so we can avoid miscommunication. Like I said, hue is the most obvious aspect of color. But while there are many ways to represent a variety of hues, Munsell chose the circle as a model for simple presentation. If we look into the history of color analysis, we'll see that this approach is now almost universally accepted. Computers must use complex equations to judge the relationships between all these colors, but a circle is simple, elegant, and ideal for what we need. You only have to define a starting point, an accepted direction, and then all the hues can be easily described by a single number. And since a circle has 360 degrees, then the hues will become numbers between 0 and 360. By convention, pure yellow was assigned the challenge of beginning our starting point on the circle, and counterclockwise is the direction of normal rotation. So with red being 0, yellow is going to be about 90, green is going to be 180, and blue would be around 270. Chroma or saturation, or the purity of a color. The combination of all the colors in that sphere that I'm talking about is really a dark, dirty gray at the center, not truly black. It doesn't go to black. We're talking about colored light when we're looking at that, not colored inks. But in the sphere of color, chroma is on a horizontal plane. It extends from that gray center point to the outside edge of pure color. Again, chroma is the purity or richness or brightness of a color, and clean colors or dirty, dull gray colors are your options. When looking at this blue on the screen here, chroma is described as a purity. It's also the intensity or the saturation of that particular blue. Now, in the graphics industry, most of the time that's described as being either cleaner or dirtier, just for simplicity's sake. Value is another term that Munsell attributed to the colors. We typically call it lightness or darkness. Lightness and darkness are normal terms for describing value, and they're tracked in a vertical plane through the sphere from top to bottom. So lightness, darkness is also useful when we're gauging film thickness differences when we're trying to correlate a proofer to a press roll. If you notice, the chroma is also affected by the light-dark attribute. So it's not possible to have both an extreme lightness or darkness at the very same time a very high chroma. The reason for this is because the very lightest and darkest of a color are near the center of the sphere, and the pure clean color is near the outside of the sphere. So you can't have those two together at the same time. Yellow is the one color that kind of stretches that more than any other color as far as being able to be at both extremes at the same time. So with these mapping systems, we've got 3 independent variables, just like latitude, longitude, altitude, or length and width. So these are a GPS for the color sphere, the X, Y, and Z axis. They can pinpoint any given color by mathematical nomenclature on each one of those. And while your hue, lightness, and chroma are all independent attributes of color, it's still true that they're physically interrelated. Specifically, it's easier to imagine a color moving in only one dimension than it is to actually force that move in practice. What this interrelatedness means is it's often going to be the cause of much frustration when, for example, a pressman just wants to darken an ink, but in doing so, he finds that the add that he does to darken it also makes it become dull, and now it's shifted hues. So when you're toning an ink, all 3 dimensions have to be taken into account, because all 3 will move at least slightly with any given adjustment to that ink. So to see color, what do we need? The first thing we need is some illumination, some light source. Now, science is going to have to reduce the physical world into a model of equations. That's just the way it works. But this is possible to create a measurement technology that'll behave much like the human eye does to changes in color. Furthermore, it makes possible the development of detailed maps that can be used to plot both color and those slight color differences. Our look into the math of color will begin with trying to outline the pieces that our scientific system characterizes. The first of these pieces is light. Light is color, pure and simple. I'm sure you've all seen light pass through a prism and create a rainbow of colors called the visible spectrum. So what is necessary to see color? We talked about we have to have a light source, then we have to have some object to interact with that light source. Objects absorb all the colored light waves except the one that represent what color that item is pigmented with. Those light waves are reflected off the object, and that's what we see as the color of that object. The same applies to naturally pigmented items or man-made pigments. So that's the reason we see a red delicious apple is going to reflect the red waves. It's going to absorb all the other color waves, while a banana is going to reflect the yellow waves while it absorbs all the other waves. So we've got a 3-part system. We've had a light source, an object, and we have to have some receiver or processor. Just like color mapping being 3-dimensional, color viewing takes 3 distinct parts. Now, the tolerances are going to be set individually in people. This is one reason why we all see color differently. A color deviation that one person regards as a problem or something that would be rejected in the print market will be considered by another, be considered fine with another person. Munsell and then later the CIE went to great lengths to determine how humans saw color. They found that we had cones and rods in the eyes, and those cones were to accept red, green, and blue. The cones signal the brain, and it processes the information to tell it what color we're actually seeing based on the amount of RGB input from those cones. Now, birds, fish, and insects have 4 cones in the eye, and they can see UV light, which is not visible to humans. So that's your trivia tidbit for today. So we have a three-part system, as I mentioned. Now, the eyes and the brain was one processor, but spectrophotometers are the other processor, and we'll consider those today. Based on some of Munsell's work, color viewing software companies again have spent much research into making their software view color as close to how the human eye sees it as possible. Within the spectrophotometer, there will be tolerances there to set for all three color attributes, the hue, chroma, and the value, plus the sum of all these differences, which is typically referred to as the DE or delta error or total error. Now, while anytime you look at color with a spectrophotometer, there's always going to be LAB values assigned to it, or L star, A star, B star, if you want to be technical. But those will all be assigned to a color, but there will only be a delta E or delta error if two colors are being compared to each other. You never have a DE if you're only looking at one color. So for color communication, for the purpose of our discussion today, we're going to be talking about how colored inks react with each other, not colored light. Munsell was dealing with colored light, as does the RGB color models that we talk about. With colored light, if you add red and green, you get yellow. With colored inks, you add red and green, and you're going to get a very dirty brown. So for, like I say, for the remainder of our discussion, we're talking about colored inks today and how they react to each other. Any two colors that are being compared are different, and they have to be described as to how they relate to each other. They're always going to be described using the adjacent color for a reference point as to what tint that color has. Now, the strength of an ink will alter how it looks as well. Cyan blue and processed blue are both made with phthalo blue pigment. So in effect, they're the same color, but processed blue is stronger and redder than cyan blue because it's more heavily pigmented. So they're truly not the same color. They are the same pigment that's in them, but they come out as a different color because of a different strength level. So talking about any of these colors is like with red, they always be described as their adjacent colors. A red can either be a blue shade or a yellow shade red, or if you're looking at two shades of red, one of them will be bluer than the other, one will be yellower than the other. The same with all the other four colors. Each one is going to be described with its adjacent colors as a descriptive factor. So adjusting the colors in the visible color spectrum. It's nice to want to stay the cleanest as possible by using the adjacent color. So if you're doing something that's not adjacent, the color is going to be dirty. For example, you take a yellow, add orange or warm red, it's going to tone it to the red side. But if you add rubine, it's going to be very far away from yellow, and that's going to make it a dirty orange. So when opposing colors are added together, there's going to be a certain level of saturation loss or dirt value that can't be removed from the formula, unlike when you use black in a formula to add dirt value. We'll discuss black's adds just a little bit later. But anytime opposing colors like blue and yellow or red and green are added together, the result is going to be a very dirty color. So you want to try to stay away from those types of color matches as much as possible. One of the first rules of color matching, keeping the viscosity correct. If you're trying to match a color that's on press and you're in a lab situation, in an ink room situation, you want to have the same viscosity on both of those inks. And you want to use the correct Analox volume. If you're trying to match a press with a 3.5, you want a 3.5 on your bladed proofer. You want to make sure your Analoxes are clean and no contamination in either situation. It's important to understand the way color hues shift when increasing or reducing color strength. If you're off in viscosity when you go to match, you're going to keep missing the mark. You're not going to match that ink. A warm red is going to go bluer as you reduce color strength, and a reflex will go greener if you reduce color strength or viscosity. A yellow will get stronger and it's going to look redder when it does. You also need an Analox at the correct volume, like I said, and it should be clean, and the ink system should be free from any contamination that will affect color. That's worth repeating. So most ink companies have SOPs to reflect what I'm talking about here. When they're making batches of ink, they control viscosity and pH first, then strength or lightness, darkness, before any color adds are made to any batch. So we want to do the same thing when we're matching color or toning inks on press. The Second rule of color matching, stay within your formula. If you were given a formula to work with, you want to try to go with that first. If you absolutely cannot do the match, then you may have to start adding more pigments. We like to stay with 3 pigments or less, or 3 colorants or less in any formula. You get outside of that and you start running into metamerism. So know your formula. If you end up with 4 or 5 different colors, then probably 3 of them don't belong. The color is not really going to match under most LAB tolerance conditions. Worse, it won't match the standard under different illuminants. If your print buyer has a particular illuminant they're looking at and you're not aware of that, and you match under a different one, you very likely can get metamerism when that happens. You want to be cognizant of what's going into the ink for matching. Colors matched using different pigments are going to have different curves that look different, just like getting 2 different routes on the GPS we talked about before. Being a 3-dimensional piece, you use 2 different routes to get your GPS. Both routes are going to get you to the same destination. But if you look at those routes as they go along, they're going to look different, just like the color will look different at different points in the light spectrum under different illuminants. And it's the same thing. Your routes don't match, the colors won't match. And actually toning the colors, as I mentioned before, cyan and processed blue are the same pigment, but a higher concentration of that blue pigment is going to change the color from cyan to processed blue. Now, that can be done 2 ways. You can have a stronger ink formula, or you can lay down a thicker film of ink. Either one is going to give you that same result of a processed blue versus cyan blue. When you are toning blues and you need them to go more green, obviously you can add green. We'll keep it very clean. You can add yellow, but again, yellow and blue are opposite each other on the color wheel, so they're going to go very dirty. If you need to go more red shade, you can add reflex blue, methyl violet, carbazole violet, or rubine or blue shade naphthol red. Now the reflex will move it to the red side while keeping it fairly clean. Violet is going to move it about twice as fast. One of the reasons for that is typically in the graphics world, reflex blues are made with a combination of processed blue and violet. So if you're trying to move something to the red side and it seems to be going too slow, keep in mind if you're using reflex blue, you're adding processed blue, which is green shade, to that color. So you're kind of fighting yourself by adding violet and processed blue at the same time. If you have pure violet available to you, that makes a much quicker method of going to the red side as opposed to adding reflex blue. Again, rubine or blue shade naphtha can go in, but they're probably going to be very dirty when you use those. So you want to try to stay away from those and use your violets. Toning greens. There's many shades of greens out there, and most of them can be made with blue and yellow. But there's some target colors that are too clean to allow that combination. Green and either blue or yellow will have to be used in, or possibly a combination of all 3 to get a particular strength level. The blue and yellow give you a very good strong green, but not very clean. And sometimes you may have to add green and blue and yellow to both achieve the strength and the cleanliness that you need for that particular color. Greens and certain reds and violets are also prime examples of colors that have a huge variation in the cost of pigments. Sometimes cost will be a factor, just the same as color and fade resistant properties. All those play into pigment selection. Color should be really matched to color and not to cost. But sometimes cost will be a factor in the matching and the printing process. We just have to be aware of that and try to deal with that as much as we can. Toning yellows. Again, you can either go to 2 sides. It can be more green or it can be more red. Yellows can be made greener with the addition of blue or green. Like I said before, green is going to be the way to go there. Any kind of blue is going to make it go very dirty. If you want to go to the red side, you've got a number of choices there. You can use orange, warm red, yellow shade red, rubine red, blue shade naphthol, barium red. The DNA orange will go slowly and it keeps it very clean. Warm red or a yellow shade red will move your yellow very rapidly to the red side, but you want to be careful about dirt value. And of course, orange is going to give you a very dirty color match are probably really going to be a brown per se more than an orange. So if you go that route, you just want to be careful with going too far away from your yellow when you're toning it. Toning reds, again, going to the more yellow side, you've got a number of choices: warm red, yellow shade red, orange, or even yellow. And again, warm red being closest, it's going to keep you very clean. Orange will move it a little faster, but again, it's going to get dirty. Yellow, once again, further away, it's going to move it very quickly, but it's going to go dirty very quickly. If you need to go to the blue side, there's rubine red, blue shade naphthol, rhodamine red, and that's blue shade rhodamine. There is a yellow shade rhodamine and a blue shade rhodamine. Violet, processed blue, or reflex blue. Rhodamine can make it go blue very quickly, but it is expensive. So you probably don't want to use that unless the original formula calls for it. Your violets, again, they're going to go quickly, but it's going to go dirty. So you want to try to use something like the blue shade red, blue shade rhodamine, that type of thing to tone the red with, to keep color correct and to keep costs down. Tone with black. Black is generally made with carbon black pigment, which tends to go brown when it's reduced, not really going to a weaker black. It actually kind of turns brown. So for that reason, blacks themselves are often toned with a red shade blue or violet to give it a stronger color. These are often called jet black or rich black. That blue will fool the human eye, but it won't fool a spectrophotometer. The spectrophotometer will pick it up and report on it. This can be an issue if you're matching to something like Grackle 7 or some other expanded color gamut profile where each of the process colors is going to be defined by specific LAB coordinates. So, and also toning with black, you can get some false strength. If you're doing a match that is going to be controlled visually, you may be able to get away with that. You want to be careful about adding too much black to try to get strength. It is false strength. It will look stronger, but you're also getting very dirty at the same time. So you want to add blacks with great caution for that reason. Finally, toning with opaque white. Opaque white will reduce the strength, saturation, and it's usually going to give a blue tint to whatever color you're adding it to. Spectrophotometer is not equipped to accept and use opaque white as an additive color, but you can become adept at predicting how a spectrophotometer will react and use opaque white accordingly to tone with. There's nothing saying you can't use it. Just like any other add to a printed ink, it's going to affect the adjusted color in all three dimensions. You need to be aware of that and kind of, like I say, be ready to predict that. Resist the temptation to use different terms to describe color changes that you may get with white, like creamy or warm and fuzzy. You want to stay with technical terms like greener, redder, bluer, more yellow, darker, lighter, cleaner, or dirtier. This will eliminate confusion and frustration during the color matching process. Now with white, as it gets more opaque, it often is termed creamy. That is a fairly common term, but again, it's not one of the technical terms. You can also make pastel colors with that, and they may help hide some film thickness variations on press, maybe gear marking, flute lines. Those are some of the common things, just surface abnormalities in a cheaper stock, maybe. All those things that are used, sometimes opaque white is used for that, but you want to be careful with it. The titanium dioxide that is in opaque white to give it its color is typically very abrasive. It's a very heavy pigment. It tends to settle in the Analox rolls. It's hard to clean out. So you want to try to keep your concentration of opaque white to the minimum to get what you want out of it, to get the most value out of it, and have as little of the downside that you get from the white as possible. So that concludes the presentation part. We'll answer any questions and answers if anybody has typed in any.
On the bottom, there's a Q&A section, and I don't see any open questions right now, and that's okay. But I would recommend that if this is a topic you want to pursue more, if there's any questions, please note the email address of the Harper Graphic Solutions advisor that is in your respective area. Additionally, tomorrow we'll be sending a follow-up email with the contact information for the technical account manager in the respective areas as well. One of the things that I did want to note is, again, this is part one of a two-part series. So we'll be doing part two of this on Wednesday, October 7th, again at 1 p.m. Eastern time, and that will pursue this topic to go on to color matching conditions. So if there's nothing else that we can help you with right now, if there is, like I said, please note the email address and the contact information of the Harper Graphic Solutions advisor in your local area, and we'd be happy to get back. Darius, we do have one question, is will this webinar be available for reference to a later time? The answer is yes. We've been working with RingCentral on utilizing recording technology. I have been recording this, and if all goes well, this has been recorded. We'll upload it to our website or to another medium that we have, and we can certainly make it available for future purposes. Darius, another question is can you talk about how LAB data between two colors, a standard and a press manufacturer, will translate to color adjustments needed?
Yes, I can, not knowing exactly where your numbers are, but when you get an LAB printout, or you get a DE or the delta difference between two colors on the spectrophotometer, you're going to have to move. If one color is saying it's more red than the comparing color, you're going to have to move in the opposite direction of that color reference it's giving you to look for your toner to move that color in the direction that you need to be to closer match the standard color. We may talk about that a lot. I can make notes of that, or actually talk more about that in the next month's color conditions. But I hope that answers your question. Basically, if you're off of the crosshair, you need to look in the opposite direction, and whatever color that is in the opposite direction, be it red, green, blue, or yellow. You need to pick a colorant, again, trying to stay within your formula, but pick a colorant on that side of the color wheel that will take you in the proper direction. I hope that makes sense.
Thanks, Darius. Are there any other questions? If not, again, thank you everyone for your time this afternoon. We hope it helped. If there's additional questions, again, please note the contact information for your Harper Graphic Solutions advisor. And like I said, we'll be sending a follow-up email tomorrow that has the name and contact information for your local technical account manager. Other than that, again, thanks for attending. Keep an eye out for the invitation coming for part two on color matching conditions. And we hope everybody has a great day.
Thanks, everyone.